I'm Brian. I'm going to do a talk about the WCN3680 on Android and Upstream, which is a very interesting project we did with Square. This is the Square point of sale terminal. It's based on the Qualcomm chipset. I won't divulge which one, but it has a WCN3680 inside of it. Which is an iteration of the WCN3620, which comes in your DB410C, and in your, well, the WCN3680 is also in the Sony M4 Aqua, and it's shipped on a whole bunch of products over its lifespan. It's really out there. For us in this, first of all, I had loads of fun in this project. It was really lots of fun and educational and successful ultimately at the end, which is always a good thing. We had two kind of targets when we were doing the development. One was Android and the other was Debian. Android because that's our production target, and Debian because that's for tests and sanity checking. And using those two platforms actually ended up being very important in terms of development and validation, as we will get into. So for those of you not familiar, Wi-Fi is not just some, well, it is a magic technology, but it's it's also a technology based on a whole bunch of different modulations and time shifting and time slicing and so on. It sits at the two bottom layers of the OSI model, at the physical and the data link layer. And what we had upstream at the time of when we initially started the project was 802.11 ABG, which is based on well, ABGN, as a matter of fact. So you could go all the way up to 72 megabits on the 5 gigahertz frequency. The DB410C has ABG, which is at best 54 megabits at the 2.4 gigahertz frequency. I don't have a WCN3660 to test with, so I don't know what sort of performance that actually gets, but the DB410C gets about 47 megabits, so it's pretty close to the theoretical maximum there. For the 3680B, it's well, the maximum for the standard is, as you can see here, 433 megabits. Qualcomm itself published a maximum of about 233 megabits, and I myself measured 230 on their downstream, so they get pretty close to their maximum with their downstream prima kernel, with their prima driver. So the prima driver is the name of the driver that Qualcomm used downstream on kernel 310 for the W6 for the 3680. Probably for the 3620 and 3660, and that driver was developed and supported until kind of end of life for that for those chips. Prima is a very featureful driver. It's also highly it's pretty out there in terms of the Linux kernel standard. If-defs, camel humping, indentation, all that standard stuff, but also bringing stuff in from the Wi-Fi stack or developing stuff inside of the driver that ought to have been in the Wi-Fi stack but wasn't available at the time. And so it's kind of very featureful but nearly impossible to forward port. So the first thing we looked at was forward porting this driver to a later kernel, and one of the problems that you're going to encounter there is removing features inside of that driver that are now inside of Linux kernel and doing it in a way that doesn't break everything. So it borders on the impossible. So what we decided in the end was to use the upstream kernel, which didn't have support for 3680 specifically. So to kind of cut a long story short, you have a base of communications with the firmware, but to add the 5G stuff onto it, you need to extend the parameter passing between the firmware, and you need to issue a bunch of commands to set the firmware up to tell it that you want to go into this extended mode. And none of that is documented except in the code. And the only way to figure it out is to do it and get it wrong and say, why is this going wrong? And go back to the prima kernel and take a bunch of snapshots of what's going on and try to understand it. So that part was slow. And of course, we comparing the upstream driver to prima and what we absolutely had to have in prima, there were a few gaps apart from just the 5G support. So one of them was I discovered after telling people, oh, this is all working, and Square came back and said, well, actually, you need to do a little bit more work here, as customers and end users invariably do, and rightly so. So one was firmware keep alive, which is where you delegate to the firmware, to the Wi-Fi chip, the task of keeping the Wi-Fi link alive between the SDA and the AP, instead of having the Linux Wi-Fi stack do that for you. That's a power saving thing. B, it's also a cadence thing. A firmware will do that on a much more accurate cadence. And C, to go into suspend and keep your link alive, you need the firmware to continuously ping the AP and say, hey, I'm here, hey, I'm here, hey, I'm here. So the first pass at suspend that we did was you would go into suspend, and when you would resume, your terminal would reconnect. If you remember kind of earlier experiences of having cellular phones, I remember a few of my phones did things like that, and I never really noticed. But if you notice now, when you turn your phone off or turn it off and put it into a low power state and turn it back on, you see that it has Wi-Fi immediately available. And of course, one of the magic things going on there is this constant firmware keep alive. But what Square wanted, and they were quite right about this, it was a guy in there called Ben, was to have a thing called ARP response and IPv4 ARP lookup response and IPv6 namespace lookup response. It's the analogous thing in IPv6 to an ARP lookup. And so what that means is you add your phone to a Wi-Fi network and you put it to sleep straight away. But if you want to send a notification to your phone, like from your bank or, I don't know, from Gmail or something like that, you want to send it to an IP, you don't actually know the ARP address of the phone on the network prior to that. So what happens is you send out your standard ARP request, and everybody does their ARP response. If you have that Mac, you do your ARP response. But of course, if your phone is in suspend, there's no IP stack to resolve the requested IP to the necessary Mac because Linux is asleep. So you need your firmware to do that. And that was another thing that we added. So those kind of three things there at the end were the last 5% of the 95%, where 95% of the effort went. This part here isn't upstream yet, but it's pretty close. The 5G stuff is upstream already. So yeah, I mean, I just went through this already. The objectives were to get to 5G, so 802.11ac speeds. So up to 233 megabits. Well, 433 was what we stated, but you know, Qualcomm themselves only said 233 megabits to have suspend and resume work. Push notifications work. So as I just explained, push notifications need to work when you're in suspend and nobody else on your network knows your MAC address. And Wi-Fi can't be a source of unreasonably high power consumption. And on that, what I'll say is it's not, but we did no specific work for that. It just turned out that Wi-Fi was not a very big consumer, and the firmware basically is doing the right thing when you go into suspend. So I mentioned briefly earlier Debian and Android. Debian, for me anyway, was for us, for our team. So Shango, myself, and Junie, two other Linaro engineers. So for us, definitely Debian is the gold standard. And in both cases, in Debian and Android, what we were working against was WPA supplicant, which is, you know, you've host APD and WPA supplicant. Those are the two most common ways of doing Wi-Fi on Linux, and WPA supplicant, of course, is, what you do when you are a client. On Debian, that runs as the daemon, and Android, what I found was they have wrapper libraries around WPA supplicant, so that if you imagine the wrapper libraries then bind into the Android services and UI. So when you click a scan, the library calls WPA supplicant, and WPA supplicant tells the driver to please do a scan. And what you have on Android is a whole bunch of vendor drivers, and therefore in the user space you have vendor-specific Android libraries that talk to those vendor drivers. Fortunately, the Android vanilla libraries don't do that. They're just kind of a standard wrapper around standard calls to WPA supplicant. So for me, then, for us in the end, to get it working on Android, if you imagine we have a delivery from Qualcomm and an Android delivery from Qualcomm with with Qualcomm specific wrappers around WPA supplicant. But when you're using the upstream driver, the Qualcomm specific libraries are actually an impediment to what you want to do, because you're never sure that when you're debugging something that you're not trying to do a vendor call that just doesn't exist in the upstream driver. So part of the work getting the upstream driver to work, which I only found out kind of in the middle of the end, was that we needed to switch out to just regular Android vanilla libraries. So that kind of leads into my gag here, which is Wi-Fi Scanning, a David Cronenberg production. I love David Cronenberg movies, don't get me wrong, but I don't want to run my Wi-Fi scan like a David Cronenberg movie. And so if you just take the difference between Debian and Android, it is a little bit like scanners. You kind of have the guy on the left with the bald head and the glasses, and that's Debian, and the guy on the right is, of course, Michael Ironside, and that's Android. And Android persistently scans. You know, it's a scan beast. You can in any given minute you can find that, you know, Android can, for whatever reason, spend 10 for example 10 seconds just scanning. They're when you open your phone up and you look for a Wi-Fi network, In Android, if you imagine it, it's just issuing a constant scan request, constantly scanning. And for roaming around between APs, it also does the same thing. In contrast to the experience you have on your desktop or with your laptop, which is you scan once, you connect to an AP, and unless the link drops, you never scan again. So that's Debian and Android, just in contrast, that's my experience of it. WCN36XX, the upstream driver, has 3 separate methods of doing a Wi-Fi scan. It has a software scan, which was already supported in upstream and is the reference for what we have from downstream. It's how downstream actually does its scan. We have a very nice hardware-assisted scan. Unfortunately, that we've only ever made that work on the 2.4 gigahertz band. We've never seen that work on 5 gigahertz. And then we have hardware batch scan, which is a kind of an asynchronous scan that runs and then delivers results, which is untested and unimplemented. So again, we don't know if it will work on the 5 gigahertz band. But if I find 2 months of my spare time, I will definitely have a go at getting that to work, because the software scan is slow and eats time, and it's really not the way you want to do things. So that's just scanning for you. Bluetooth, in contrast, just works. It was a very easy experience. All of the upstream work for WCN3680 just worked. It's a credit to whoever did it. Fair play to you. Thanks very much for your hard work. It was a total no-op for me. In terms of results, so the WCN3680, we can get onto the correct 5 gigahertz, 80 megahertz MCS9 connection to the AP. We're only getting about 130 megabits instead of the 230 megabits. I don't know why. So we're getting about twice the speed of the 3620, actually over twice the speed, maybe 3 times the speed, 2.5 times the speed. So it's a definite improvement in terms of throughput, but there's definitely a large gap that needs to be filled there. Suspend resume, on the other hand, works and appears to work very well. And the good news is for 3620, suspend resume also works there, as does the IPv4 ARP lookup and the NS6, the equivalent, what we call WoWLAN, Wacom WLAN. WoWLAN sounds cooler. So it's the work that we did on 3680 is also beneficial to WCN 3620 and 3660. Of course, to do suspend and resume, you do need additional patches to do it properly. You need additional patches for the core because the low power mode on the relevant chipsets isn't upstream, but that's neither here nor there. So yeah, I'll draw your attention to the graphic here. You can see I'm not making it all up. This is my Square device with a fairly recent kernel on 5 gigahertz at 80 megahertz. So that's probably not MCS9 there. It's in some quiescent mode. Next steps, though, for me would definitely be thermal support. Maybe some of the reason that it's slower than on downstream is we haven't implemented any of the thermal support. So whatever the default thermal mode is, and presumably we can tell it to go faster. A really interesting thing is called radar detection. So if you are an AP, it is your responsibility to detect when there is radar on your band and switch all of your client devices to another band. And to do radar detection, I would have to go up to the airport and sit there with a thing in my hand, pushing buttons beside the radar dish, I'm sure security would have no problem with that. Wi-Fi Direct, nobody really wants that feature. I don't think that works too well in upstream or how well it's supported, but it's certainly interesting. And Wi-Fi batch scanning. So I think I have to end the session now. Thanks for bearing with me there at the start. And I'm available to take any questions you might have in the relevant forum.